Welcome to the second part of Lecture 4 of ECE 141. It's still an introduction to digital modulation, but at this point of the lecture, you already know your pulse amplitude modulation. How do we represent your bits back to symbols? How do we transmit them? And so on and so forth. By now, you already know amplitude shift keying or ASK and phase shift keying or PSK. And if we combine the two, well, we have some more unique combination of symbols in our constellation. Right? So now let's try to generalize that. So from our PSK, which has a dimensionality of 2, now we have what we call the quadrature amplitude modulation. So let a PAM signal ride each element of the basis of PSK. Right? So with that, your cosine and your sine functions now carry two PAM signals right here, an in-phase component and a quadrature component. We call this quadrature PAM or QAM, quadrature amplitude modulation. With this, we can now express this form of the signal. We don't want this. We want to express it in terms of your orthonormal basis. And we get this function right here. So recall that the orthonormal basis for your cosine and your sine, for cosine, okay, and I don't know what's happening there. So let me try to fix that. So for your cosine, okay, that's phi 1. Phi 1 of t is equal to the square root of 2 over the energy of your pulse times cosine of 2 pi fct. So you already get that. Alright, so now we know the breakdown or the analysis or the your symbol signal represented as a sum of its orthonormal basis functions. We can now convert that to a vector. And we have this expression right here. So this is your in-phase component, this is your quadrature component. How do we plot this? Let's say we have 4 values for each symbol. With that, we have a 4x4 grid, and this is the mapping of your quadrature amplitude modulation. Right? The distance between two neighboring symbols is equal to this expression right here. It's similar to ASK. But the average energy per symbol is equal to this equation right here. Right? So we notice that, well, compared to ASK, let's look at some comparisons. Using the same minimum distance, quadrature amplitude modulation uses less energy compared to your amplitude shift keying. Okay? Uses less energy generally. Well, it depends actually on your M. Right? So, to summarize, when you compare ASK, PSK, and QAM, or QAM, so this is the summary of the minimum distance and the average energy per symbol. So note that we want to reduce the amount of energy we transmit. And also, we want our minimum distance to increase. Okay? We want our minimum distance to increase for a more reliable communication system. How do we compare the different symbol mapping methods for our memoryless modulation methods? Well, we can compare them using the minimum distance, but we need to set a common ground for this E sub g right here. So E sub g actually changes. It depends on the average. E sub g here is actually what do you call this? It's an argument for the function of your energy per symbol. Okay, so I hope that was clear. So your energy per symbol rather is a function of your E sub g. But this energy per symbol actually kind of depends also on the number of elements in the constellation. Maybe it's best if we compare them using the energy per bit, E sub b. So E sub b is equal to, recall, your energy per bit is your energy per symbol divided by the number of bits. Alternatively, your E sub s is just L times E sub b. Okay. So by substituting that, knowing that m, the number of symbols, is equal to 2 times 2 raised to the Lth power, or 2 raised to L. Then the number of bits is equal to log of the number of symbols base 2. So I won't complete that. And we get these resulting functions right here. So for ASK we have this, PSK we have this, and QAM we have this. Okay. So comparing them, it's better to compare them graphically. There we go. So for different bits per symbol, number of bits per symbol, your minimum distance varies. Turns out that QAM is the best choice for the symbol mapping. What does it trade off? It's a more complex system. Your ASK, recall ASK is one-dimensional. PSK can be easily demodulated because it's just tracking the phase of the signal. But QAM right here, we need to know the phase and the amplitude of your signal. Okay? So basically, you're trading off complexity for a greater minimum distance. Right? But generally, QAM is, in terms of minimum distance, QAM is better. Okay? So it has greater minimum distance compared to your ASK and your PSK. Okay? And that's summarized right here. So in general, when your M increases, if we fix the energy, your minimum distance decreases, which decreases reliability, etc., etc. Basically, there are just a lot of trade-offs. If you want to increase your reliability, you need to increase the energy. Okay, and QAM is what I said earlier, generally more reliable than PSK and ASK, but it's more complicated to implement. And if power is limited in the channel, we're already constrained with a certain performance level for our QAM, PSK, and ASK. Alright, so if that is the case when power is limited, so when power is limited, maybe we can use more bandwidth to transmit signals. Okay, but QAM, ASK, and PSK has a fixed bandwidth. How do we increase the bandwidth of a signal and limiting our power? So let's recall. We have amplitude. We're varying the amplitude. We're varying the phase. What if we vary the frequency? That is our frequency shift keying. So consider a frequency spectrum of a bandwidth of m delta f. Okay, and we divide that into m frequency bands. So basically, we transmit a symbol on a certain frequency band, and when you receive that frequency, then you get your symbol. Okay, so different symbols on different frequencies. All right. All right. So if we use the same basis as PSK and QAM, we can represent this in signal space. So we just expand this expression right here, and we get this with this. So the vector representation of an FSK signal is, wait, it's time varying. Should they be time varying? If you're looking at a constellation, your signals should be stationary. But for FSK, your constellation is time varying. How do we make sense of that? Well, we're looking at it at the wrong way. We actually need to define a different basis for our FSK signal. Okay, so let's say that each individual symbols are orthogonal to each other. So using the complex baseband equivalent, so we can just represent them as complex baseband. We can simplify the calculation and the derivation, etc., etc. So if you're using that, then we need to get the inner product between your two different frequencies. And if we want them to be orthogonal, then their inner product should be 0. So your integral simplifies to, so this is just a simple integral. That's just your natural exponent. And when you get the real part of that, you get this expression right here. Okay, sorry, not real part. When you simplify that, you get this expression. And this is actually a sinc function. Okay? And the sinc function, when will that be 0? It will only be 0 if, okay, basically your frequency spacing, the spacing between your 2 points or your 2 symbols, is an integer multiple of 1 over 2t. T here is the symbol period. So this is the condition at which your 2 signals are orthogonal. And since we have m different signals that are orthogonal to each other, we create an m-dimensional space. Right? And our basis functions depend it's actually signals. Your basis signals are actually signals of different frequencies, rather. So they create an m-dimensional space, and this is your basis function. And we have m elements of that basis function. How do we look at it? Well, it could look like this. Your constellation has 4 dimensions if you have 4 symbols. Right? As always, we want to know the minimum distance and the average energy. Right, so if we're gonna break down your different symbols, since they are orthogonal to each other, then the different symbols have a value or have a value square root of e depending on what dimension they are. So let's say S sub 1 lies on the first dimension, S sub 2 on the second, and S sub m on the mth dimension. Then correspondingly, the square root of e is placed as such. So the distance between any two symbols are equal. So the distance from here to here is equal. The distance from here to here also equal. The distance from here to here the same. From here to here is equal, equal, and equal. Okay? So why is that? It's because they are orthogonal. Okay? So the minimum distance between the two symbols is square root of 2e. And we want to know the average energy per symbol. Okay? Since all these symbols are orthogonal, then basically E right here defines the average energy per symbol. Right? So the energy per symbol between symbols S1, S2 up to S sub m, all of them have equal energies. If you get the average of that, just get your energy E right here. And this is the energy per symbol, and we express that as an energy per bit. We finally get a minimum distance of this function right here. Okay. So the drawback of FSK is that it uses a lot of bandwidth. So again, by our definition of FSK, we need a bandwidth of m delta f. So if you want more signals, you need to sacrifice more bandwidth. But the good part is power. If the power is limited, we can cram more symbols even if the power is limited, as compared to your QAM, FSK, and PSK. But we're not satisfied with that. We're not satisfied with that. Maybe we want to save more bandwidth. We can use what we call bi-orthogonal signaling. So to save bandwidth, less dimensions must be used. Maybe we could reflect all of our signals. So instead of just a positive version of the signal, maybe we can put a negative version of the signal in our constellation. So the resulting constellation would have twice the number of symbols as compared to your original constellation. So something like this, as you can see, from your 3, and you want to reflect that in the other side of their respective dimensions, you get the resulting constellation. Right? And with that, we're also interested in their minimum distance, energy per bit, etc., etc. So their equivalent signal space vectors would be what is shown in the screen right now. So we have two symbols on each dimension, and each symbol has energy E. It's the same since your reflection right here, okay, the reflection right here has the same distance from the origin as your original signal, but only the negative of that. So we have the same symbol energy E. In one dimension, between two symbols, the distance is 2 square root of E, but that just means that this distance is greater than the distance between two symbols, okay? So that are on different dimensions, right? So it's still the same. The minimum distance is square root of 2E. And we want to know the average energy per bit. Okay. So this should be still E sub B times log M base 2. Okay. And then the minimum distance is the same as your orthogonal signaling using FSK. Okay. So what's the trade-off there? It has the same minimum distance. Well, you have a more complex system. You need to detect if it's a negative carrier or if it's a positive carrier. So that's the difference. So there are always trade-offs when you're considering systems, all right? So as engineers, you need to find the balance. All right. So another type of multidimensional signals is what we call the simplex signaling. So consider a set of M orthogonal signals. We get the mean of the set. So just get the mean of all your orthogonal signals. And a new set of orthogonal signals can be derived by shifting your original signals by the mean. Okay? We're shifting the all of our orthogonal signals, our orthogonal symbols by the mean. Okay? So the minimum distance between orthogonal signals, since this is just an origin shift, the minimum distance is the same. So this is a visualization of what is happening. Okay. So I have three signals. We get their mean, which is the centroid of the triangle that they form for this. And we shift the set of symbols such that the middle of these three symbols is the origin. So this is your simplex signaling. What's the advantage of simplex signaling? We actually have a reduced average energy. So using symmetry, we can solve for our average energy per symbol. So the average energy of each symbol is the same. That is equal to your original symbol minus the mean and then their norm squared. So this is a definition that you learn from vector spaces. And you solve that, you get this expression for the average energy per symbol. So as compared to your as compared to your orthogonal signaling, we have a factor of -1 over m here. Right? So we are now interested with the minimum distance as a function of your energy per bit. Thus, the expression for the minimum distance becomes this expression right here. Right, so I think there's something wrong there. There should be E sub B inside. Okay, there you go. Oh, yeah, it's right here. All right, so just for comparison, okay, so your FSK by orthogonal signaling and your simplex signaling, these are the minimum distances as a function of energy per bit. And comparing them to what we have earlier, oh, would you look at that? If our ASK, PSK, and QAM decreases with the number of bits per symbol, our FSK or bi-orthogonal signaling and the simplex signal actually increases in minimum distance. So basically, if we want more symbols, we actually, if we have more symbols rather, we actually increase the reliability of FSK and your simplex signaling or your multidimensional signaling. What is happening right there? What are we trading off? We're actually trading off bandwidth. So if, again, if we recall from FSK, uh, a frequency band of m delta f defines the FSK signal. However, if we want to have more symbols that for our constellation, we need to increase the bandwidth. Even if the power is limited, that's fine. We just increase the bandwidth, we get more symbols. Right. Turns out that if we increase the symbols more, then we create a signaling system that is more reliable each time. Downside is we just spend more bandwidth. So those are the challenges that you face when you're designing these systems. When you just design a symbol, there are so many considerations already. Consider the minimum distance between the symbols. You consider how much power they use. What are the trade-offs? Basically, it all depends on you. You need to be able to study the channel, create a constellation that is suitable for the channel. It depends on the application. Right, so I'll just leave you with some remarks. This is the summary of what we talked about. Basically, M increases, minimum distance of your multidimensional signals increase reliability, but you're trading off bandwidth. Okay? Compared to QAM, ASK, which are bandwidth limited. Okay? So now we're gonna differentiate them. QAM, ASK, and PSK are called bandwidth limited signals. Okay? So you have limited bandwidth, but you can transmit at any power, then you can just use QAM, ASK, and PSK. Okay? But your multidimensional signals, right? These are what we call power limited. So if you're limited in transmit power, then you can consume more bandwidth so that you can cram more symbols. Right? So basically, there's some form of trade-off. If you have greater bandwidth and you can just reduce the power, so you can have the same reliability. But if you decrease the bandwidth, you need to increase your power such that your system is more reliable. Okay? That's the key takeaway between these two signal schemes. Basically, what you observe, aside from learning all these QAM, ASK, PSK, FSK, bi-orthogonal signals, simplex signaling, etc., etc., well, you observe some form of trade-off between bandwidth and power. This is actually, I believe it's not seen in analog signals at all. For digital signals, you consume more bandwidth so you can reduce the power or vice versa. Okay? So that's the end of this lecture. I hope you learned something. Okay? So this is also the end of lecture 4. And if you have any questions, comments, suggestions, maybe for my teaching right here, for maybe my explanations are not clear, please tell me. Okay? I'd be happy to get any suggestion from you. So still the same, if you have any questions, I'll try to answer it as soon as possible. Thank you for listening. I'll see you next lecture.